Michelle at some point is going to put some codes on the chat. That shouldn't take away your focus from your presentation, but she needs to do that for people to get a CME credit.
I completely understand.
We'll wait for about 1 more minute and then start with introduction.
That would be great. Thank you.
Thank you. Good morning, everyone. It is thank you for joining us for Medical Grand Rounds. It's my pleasure to introduce Dr. Adasi, who is a physician, scientist, educator, and visionary leader in ethics as well as in science. Dr. Adasi's journey began in Haifa, Israel, where he was born to parents who had fled the turmoil of pre-war Europe. He was the only child of a dedicated kindergarten teacher and engineer. And Dr. Adasi was educated and driven to science and medicine. He was a proud member of the first graduating class of the Tel Aviv University School of Medicine and earned his medical degree there before coming to the US to study obstetrics and gynecology at Tufts University. Then followed with specialized fellowships in reproductive endocrinology and reproductive biology at Johns Hopkins and the University of California, San Diego. Dr. Adasi's academic career took flight at the University of Maryland, where he directed the Division of Reproductive Endocrinology before stepping into leadership as acting chair of the Department of Obstetrics and Gynecology there. His leadership, innovative vision, and commitment to academic excellence then took him to the University of Utah, where he served as the John A. Dixon Presidential Professor and Chair, and where he founded the Ovarian Cancer Program at the Cancer Research Institute there, a program that continues to impact lives today. In 2004, Dr. Adasi took on one of the most defining roles of his career as Dean of Medicine and Biological Sciences at Brown University. His tenure there was part of a dramatic transformation of Brown's medical school, from a curriculum modernization and an establishment of new scholarly programs to the expansion of the student body, to the creation of dual degree programs, and to a historic 100 million gift that laid the groundwork for the Warren Alpert Medical School's home and transformation over the next generation. Brown rose in national rankings under his leadership. Beyond his academic leadership, however, Dr. Adasi has been a trusted voice in health policy and global health, serving as the senior advisor of global women's health at the US Department of State, and advising organizations such as WHO, the World Bank, and the Bill and Melinda Gates Foundation. A member of the National Academy of Medicine, a fellow of the American Association for the Advancement of Science, and the recipient of numerous honorary degrees and awards, Dr. Adasi's impact expands across different fields and different generations. He has published more than 700 peer-reviewed publications. He has mentored dozens of postgraduate fellows, and his editorial leadership has impacted major journals. Dr. Adasi, welcome, and we're delighted and looking forward to your presentation.
Thank you, Lefteris, and it's good to see you again. If I can say, if we can refer to this encounter as seeing, but I see your image, and thank you for the opportunity.
Thank you.
Today we will talk about the future, It's not quite here yet, but it seems inevitable, and it does seem to represent a marked departure from what we have been used to before in terms of artificial reproduction. I don't think I need to remind this audience that IVF began in the United Kingdom and was first reported on the pages of Lancet in 1978. Louise Joy Brown, who was born as a result of that early IVF attempt in 1978, graced the front page of Time magazine and many others, as we can all anticipate and imagine. The main protagonist, as you probably also know, was Robert Edwards, PhD, who ultimately received the Nobel Prize Award for this development of IVF in 2010. His two key collaborators, Dr. Patrick Steptoe and Ms. Jane Purdy, did not share in the Nobel Prize, unfortunately, because they have passed away by then. And it is the policy of the Nobel Committee to limit the award to living recipients. Dr. Edwards himself passed away in 2013. In the United States, we were somewhat lagging in that department, but caught up eventually at the end of 1981. The protagonists in this case were Doctors Howard and Georgiana Jones, formerly from Hopkins, who moved to Norfolk to establish an IVF program, the first in the US. The success of which was marked by the birth of Elizabeth Jordan Carr, who was the first American IVF baby, shown here on the pages of the Boston Globe and even on the front page of Life magazine. The team that made it all happen is shown here. But going forward, IVF is likely going to be replaced by so-called in vitro gametogenesis, the beginning of which transpired in Japan under the leadership of Mitinori Saito from Kyoto University and Katsuhiko Hayashi from Kyushu University. At the time I met the two, which was in 2013 or thereabouts, they still work together. Professor Hayashi was working at the time as a postdoc, and only later branched out to establish a program of his own. The experimental paradigms, as is usually the case, involve the rodent and the human. And it is all, of course, dependent on the existence of pluripotent stem cells, a relatively recent discovery of cells that essentially can become anything. They come in two varieties, as you know, embryonic or induced. In theory, we could replace any cell in the body if we knew how to create a substitute. For example, we could replace amacrine neurons in the retina in congenital cases of their absence. We could potentially replace dopaminergic neurons in the striatum, perhaps in cases of Parkinson's disease. And who knows, we could potentially replace motor neurons in the spinal column in cases where paralysis has set in for one reason or another. But today we will focus on the creation of gametes from stem cells. But as I try to emphasize, gamete is just one fate of stem cell origins. We can, as I said, imagine virtually any cell type in the body at one point or another being created from a stem cell origin. Science magazine recognized the import of this work and dedicated to it a special spread in 2021 with the two Japanese protagonists being the authors. The New England Journal of Medicine, not to be outdone, solicited a comparable work from two British investigators and published the same in 2022. More recently, in 2023, the National Academy of Medicine convened a workshop that was dedicated to in vitro gametogenesis, and it is likely that a consensus committee report may follow at some point. I had the privilege of chairing that workshop and guiding its formation and its execution. As you may know, the Nuffield Council on Bioethics constitutes the leading ethics institution in the United Kingdom. And it says aplenty when it becomes apparent that the first topic they plan to study in the coming year is in vitro gametes, in vitro-derived gametes. Yes, they also focus on time limits, on maintaining embryos in culture, on womb replacements, on preconception screening, and the like, including egg freezing. But at the top of their list are in vitro-derived gametes, which goes to show, I think, the currency of the topic, the excitement that surrounds it, and the likelihood that it will materialize in the next decade or two. I think we can all agree that in vitro gametogenesis is a disruptive technology. Whether or not it's achievable in the human, of course, remains to be convincingly demonstrated, although we are very close, it seems. And the timeline, as always, is somewhat uncertain. But if I had to predict, I would say in a decade or two, we will probably be there. At this juncture, it is good to recall the work of Aldous Huxley, who published his work in Brave New World in 1932, wherein he made several predictions. One of them was that eggs will be produced via ex vivo ovarian cultures. Not quite IVG, but close. He also predicted, and was right on, of course, that embryos will be created via in vitro fertilization. He also made the prediction, which is yet to materialize, that newborns will be born via ex vivo ectogenesis, which is to say that women will be relieved, if you could call it that, of the responsibility of carrying and delivering a conceptus. As I said, the one prediction that is already obviously very much real is the prediction that embryos will be created via IVF. If you go back to the book and take a read of chapter 1, the so-called director of hatcheries and conditioning says, 1 egg, 1 embryo, 1 adult, normality. Making 96 human beings grow where only 1 grew before, progress. Now, the very concept of in vitro gametogenesis, not even the practicalities thereof, faced a number of early obstacles, the most significant of which was the so-called soma germline barrier hypothesis, which was formulated by Professor Weissman from the University of Freiburg back in 1893 in his book, The Germ Plasm, A Theory of Heredity. According to this book and many teachings that followed, the germline was indeed destined to give rise to the soma, and the germline, by dint of that, could be thought of as immortal. On the other hand, the idea that the soma could give rise to the germline that would be mortal was considered anathema and unreal and unachievable. But that's exactly what in vitro gametogenesis is all about. You take a skin cell, and through a series of in vitro manipulations, you convert it to a gamete. And we will show examples of that in just a minute or two. Now, as I said earlier, none of this would have been possible without the development of pluripotent stem cell formation technologies. And just to refresh your memory, there are 2 ways of producing pluripotent stem cells. The first, historically, was the so-called somatic nuclear transfer technology, or SCNT for short, which dates back to 1958 and is attributable to John Garden from the UK, who published his ideas in a Nature paper in 1958. In essence, he started with a somatic karyoplast, transfected it, if you will, with an oocytic cytoplast, and created a quasi-zygote, which developed into a blastocyst and produced an inner cell mass, as is usually the case, from which he then derived embryonic stem cell. In 2006, an alternative and simpler technology was introduced, the so-called induction technology, attributed to Shinya Yamanaka, MD, PhD, also from Kyoto University, who published his paper in Cell in 2006. This is the technology most everybody uses today, and it involves starting with a somatic cell, transfecting such with select transcription factors, and giving rise to induced pluripotent stem cells that can then be taken anywhere, including, hopefully, towards a gametogenic fate. Both individuals, most appropriately, received the 2012 Nobel Prize in Physiology and Medicine because of the wide range of applications that this gave rise to. We will only be discussing today gametogenesis, but as I said, so many other cell types could be produced and potentially replace deficient ones, that this technology is truly a breakthrough, the likes of which we don't run into very frequently. So to focus now on in vitro gametogenesis, what we are saying is that we could start with a somatic cell, say a skin cell, and then convert it either to an embryonic or induced pluripotent stem cells by the technologies we just described, and then guide that stem cell towards a gametogenic fate. What would it take? In other words, what are the prerequisites? Well, you would need to know the cellular hormonal cues that need to be applied to that skin cell, the sequence by which these signals would have to be applied, the timing thereof, and the niche in which the cell is embedded. By that I mean the following. As everybody in this audience knows, oocytes are surrounded by granulosa cells and by theca cells, which we refer to as the niche. That is to say, the somatic cells that continuously interact with the germ element and make it possible for it to mature. The same is true for the Sertoli cells, which surround the sperm and play a major role in the maturation thereof. So the beginning of this field, which was very modest, can perhaps be traced to 2003, when a science paper described the derivation of oocytes from mouse embryonic stem cells. The leading author at the time was a postdoc at the University of Pennsylvania, but is now the director of a Max Planck Institute for Molecular Biomedicine in Germany. That same year, a Japanese investigator, on the pages of the Proceedings of the National Academy of Sciences, by the name of Toshiaki Noche, reported the same findings. Moreover, George Daly, who is presently the dean of Harvard Medical School, published in Nature in 2004 on the derivation of embryonic germ cells and male gametes from embryonic stem cells. And René Rehopera, who was at the time at UCSF, published in Human Molecular Genetics, more of the same. As we go through the years between 25 or 2000, 2010, more papers have seen pressed in leading journals, and the same is true for the decade between 2010 and 2020. Significant papers, significant journals progressively made it clear that in vitro gametogenesis is just a matter of time. And when we stop and think about where we were in 2015, we can say that at that point, the germ cell specification pathway was not shown to be conserved between the rodent and the human, and so we had to figure out the human counterpart. And the genetic networks involved were also quite distinct. So it wasn't going to be easy, but I still think it was going to be inevitable. In essence, we knew how to take embryonic stem cells or induced pluripotent stem cells, convert them to primordial cells. What we did not know how to do is how to convert the latter to haploid post-meiotic mature gametes. In a word, we mastered the extragonadal component, but we had yet to master the intragonadal counterpart. And so the final frontier remained, conducting in vitro gametogenesis all the way. This was ultimately first accomplished by the now familiar Katsuhiko Hayashi, who published on the pages of Nature in 2016 a paper titled Reconstitution in Vitro of the Entire Cycle of the Mouse Female Germline. He started off with induced pluripotent stem cells, or stem cells in general, combined them with primordial germ cell-like cells, converted them to primordial germ cell-like cells, combined them with somatic gonadal cells, and ended up producing primary oocytes, eventually M2 oocytes, which are shown on the left lower hand side, which upon fertilization and blastocyst formation gave rise to pups. In a word, he took the process for the first time all the way, albeit in the rodent. Much of the same transpired in the male, this time courtesy of Professor Michinori Saito, who published in Cell Stem Cell on the in vitro reconstitution of the whole male germ cell development from mouse pluripotent stem cell. And so we could say by 2021 that in the rodent, at least, IVG has been taken full circle. But in the human, we're not quite there yet, as I will try to illustrate in the next few slides. Probably the most advanced paper in this area is this science paper by Michinori Saito, which was published in 2018, wherein he begins with the induction of human primordial germ cell-like cells, combines them with somatic cells, and proceeds to create what amounts to oogonia, but not M2 oocytes, which is really what you would need if you wanted to fertilize an egg and create an embryo. And so the terminal stage, if you will, of that sequence is still missing. But knowing what we know about the remarkable ability of these Japanese investigators, I have little doubt in my mind that it's just a question of time before in vitro gametogenesis will be taken all the way. I find it peculiar and puzzling that there is very little of this work being carried out in the United States. This may have something to do with NIH regulations, but it's still somewhat surprising that for the most part, much of this work still is conducted in Japan. Even work that is done in the United States, for example, on the reconstitution of spermatogonia, is led by Kotaro Sasaki, who is affiliated with the University of Pennsylvania, which is probably the only site where meaningful work is being carried out in this arena in the US. Now, the notion of creating M2 oocytes or spermatozoa from in the human via in vitro gametogenesis is really where we are now at. And it's not difficult to see the scientific and translational process of a successful realization of this vision. In terms of advancing science, this will, of course, provide us with an inexhaustible supply of germ cells. It will allow us so-called functional or now mutant analysis, wherein we can knock out one gene at a time and ask, what does it do to the function of the cell? It would allow us to study germ-somatic cell interactions in vitro in ways which would have been difficult before. And on the clinical end of things, it could allow us to reverse germ cell failure in men and women who, for one reason or another, suffered an injury to the germ cell compartment and are therefore sterile. We could think of autologous gamete replacement, potentially gene editing in cases where the genetics is defective, so gene-edited gamete replacement. And amazingly, and again, very surprisingly, but now quite realistically, the notion of same-sex parenthood, by that I mean genetic same-sex parenthood, which obviously still require a female surrogate to carry the embryo. But the notion that we can now change by in vitro gametogenesis even the sex of the gamete is behind papers that have now seen press in Nature and elsewhere, mostly by Katsuhiko Hayashi, which have introduced a whole new dimension to reproduction, and all due, of course, to the courtesy of in vitro gametogenesis. We have a separate lecture on that because it's a whole new field that deserves specialty treatment. But in terms of what IVG does to IVF today, or will do to IVF in 10 or 20 years, it will essentially eliminate the need in hormonal stimulation of women and the need in egg retrieval, because you will be producing the egg probably from a somatic cell. It will also do away with gamete donation, for which we have banks these days, sperm banks, egg banks. Probably will not be needing those. And it will largely convert IVF to a laboratory procedure, although we will still have to transfer the embryo to the uterus for subsequent gestation, but much of what precedes it will have been rendered redundant. Yes, we will still have to prepare the endometrium, and I said, and transfer the embryo, but for the most part, the complex process of IVF will be substantially simplified. In theory, this could improve affordability and therefore access by individuals who either lack insurance or cannot afford the process. The only caveat I will add here is that somehow we in the United States always found a way to jack up the price one way or the other. And so whether or not this possibility is real, time will tell. Finally, and I'm sure this audience is fully cognizant of this issue, all of this will have to come under FDA jurisdiction if it ever comes to light. The area in the FDA that is responsible for the vetting, regulation, and approval of IVG is the so-called CBER, or Center for Biologics Evaluation and Research, which is headed by Peter Marks, MD, PhD. In their lingo, IVG will fall under the heading of HCT/Ps, or human cells, tissues, and products. But once it receives the blessing of FDA, we are off and running, and the notion of in vitro derived gametes will no longer be a future promise, but rather will be a reality that our children and grandchildren are likely to take advantage of. So these are going to be gametes to order, a new day that at this point is still somewhat speculative, but by all indications is inevitable. So for now, I would say stay tuned. I will close here, and I will be pleased to entertain any questions if there are any. So thank you very much again, Lefteris, for the opportunity. It's good to see you, and I hope I contributed some to your new home.
Thank you, Dr. Dassi. We appreciate having you. I would like to start with a question about how do you foresee IVG combined with CRISPR and other technologies, and how this is going to affect and what safeguards will be needed for designer babies, is the question. Thank you.
Right. Well, I think it's probably wise for both of us to stay away from designer babies. But in terms of real pathology that needs to be addressed, there is no reason why in vitro derived gametes could not be subjected to CRISPR to correct an inherent genetic pathology should such exist. That really hasn't happened yet, of course, because IVG hasn't happened. But there are examples now of IVF wherein a genetic pathology was addressed by CRISPR technology to the degree that it is available and developed at this point. I think we all are still cognizant of the limitations of CRISPR. It can do many things, but it's not quite yet where I think its full potential is realized. But there is no barrier in principle to applying CRISPR to IVG and to combining those technologies in the years to come.
Thank you. Dr. Jackson goes one step further with his question. Dr. Jackson, do you want to verbalize your question?
Unmute myself. Terrific lecture, Professor. Thanks so much. So do you think that IVG eventually will reduce the risk of genetic abnormalities and also diseases?
Well, thank you, Dr. Jackson. I mean, only to the extent that it will give us ready, convenient, workable access to gametes before they are either fertilized, let alone replaced in the uterus. And so, yes, I would say, subject to the development of technologies that are in a position to rectify inborn genetic pathology or other difficulties, yes, I think we are entering an era where reproduction is far more accessible and therefore addressable in terms of whatever genetic deficiencies or other it may bring to the fore. So yes, I would say in principle that is very likely. I hope to be around when that science paper is published.
Thank you. And could you comment on what is going on in Israel with I remember a couple of years ago, we had a fabulous lecture about how the Israeli physicians were able to focus in on certain genetic diseases. And I believe they were doing some in vitro manipulation in order that the parents would not be carrying a baby who would eventually succumb and suffer from, I believe it was Tay-Sachs, but I may be wrong.
Yeah, I have to confess, my origins notwithstanding, I'm not specifically familiar with that work, but as I said, it is feasible or becoming feasible. And there is little question but that science in Israel has always kept pace, although it often relied upon and drew upon international science, including in the US, by individuals spending time in postdocs and the like outside of Israel. So I wouldn't be surprised. Israeli scientists have been creative and forward-looking. I'm not personally familiar with specific work along the lines you mentioned. Would I be surprised? No. But I will pledge to do the following. After we hang up, I will do a search and see what we can find in that respect, because that would be a noteworthy observation.
Thank you, Dr. Darcy. Dr. Taffet, you have a very good question about epigenetic reprogramming. Do you want to verbalize it?
Sure. Dr. Dashi, first of all, that was wonderful and very thought-provoking. Do you think there's the opportunity not only for DNA editing, but even epigenetic editing so that we could erase the past misfortunes of our experience from our donation into our progeny?
Yes, I would say it's just a question of time, in my view. Once you make the target cell accessible, and once you develop the insight into epigenetics, and more importantly, the ability to modify some epigenetic markers, there's nothing that stands between us and a brighter future in this area. It was all, in reproduction at least, contingent upon having gametes conveniently accessible in a dish wherein we could apply the technology we are developing elsewhere. Up until now, it was all, as we know, an in vivo process. And because of that, we were really limited in our ability to influence the outcome. For the first time in history, we now have taken the process of fertilization and early gametogenesis in vitro. And once that happens, in principle, every valid FDA-approved scientific technology that we consider to be moral and acceptable could now be applied. And I would include epigenetic modification in that context. I don't think anything along these lines has been attempted, even in the rodent. But in my mind, it's just a matter of time. And I say so in part because I have met in person the exceptionally talented Japanese investigators who are making this field happen, and having chaired and initiated the National Academy of Medicine workshop a year ago. So I am very optimistic that many of the maladies that heretofore were inaddressable and we had to either resort to termination or accept the outcome. I think much of that going forward will be, a thing of the past, or at least that is my current hope and conviction.
Thank you.
Dr. Adasi, how, if reproduction can be based on non-gonadal cells, how do you envision this will change family, the sense of genetic parenthood and consent?
Well, of course, you would need to consent. Anybody and everybody, when you engage in a process that is so fundamental to human biology and existence. But since the people who come to seek advice and assistance and who are unable to conceive otherwise, or are unable to conceive a healthy child otherwise, I think most of us will look upon that approach favorably, subject to FDA approval. To me, this would come across as a morally justifiable approach that is very much in keeping with the Hippocratic tradition and oath with which you are more familiar than I am. But we abide by it, and we feel that it is critical to, obviously, all of us who are probably in this room or listening to this lecture have all taken the oath, and all, I think, are here to alleviate suffering, correct deficiencies, and allow, most importantly, in this case, the birth of healthy children.
Thank you, Dr. Adasi. I don't see any other questions. I'll wait for a few seconds. I thank you for this stimulating talk. This was fantastic. It was wonderful to see you, wonderful to learn, and there is a lot of excitement and a lot of concern about this technology as well, and we learned a lot about it. Thank you. We appreciate you joining us and giving us our medical backgrounds this week.
My distinct pleasure.
Thank you. Thanks everybody for joining. Bye.
Bye-bye.